it's fairly common to see these sorts of problems in a numerical approach as well. In other words, when you're given a table of values, some people like to go ahead and plot the graph so that they can draw the pictures of the rectangles or the trapezoids. I think that's a great idea. I'm not going to do that in this video because I think it might take too long to do that, but that's definitely a good option, especially for those of you who like to see that visual approach. But yeah, really what we're looking at here is finding an approximation of the same value 3 different times, and we're going to use the 3 different methods that are possible here. Notice the RRAM and the LRAM and the trapezoidal methods are the 3 methods we're using. Why aren't we doing a midpoint? Well, with a table of values, it becomes very difficult to do midpoint. For example, if I wanted to use the height of a rectangle that goes from x equals 0 to x equals 3 using the midpoint method, then I would need to know the height of the rectangle of the function at x equals 1.5, exactly halfway in between those. So normally we're not going to use MRAM with tables of values. Sometimes you might see that happen where we could do maybe two rectangles, maybe one going from 0 to 5 with the midpoint of 3, and then one going from 5 to 12 with a midpoint of 9. Of course, 9 isn't the midpoint of 12, but 5 and 12. But at any rate, we're not going to mess with that here. We're just going to use RRAM, LRAM, and the trapezoidal method. So with RRAM, our first subinterval is going to be 0 to 3. The delta x value is going to be 3. Then our next interval is going to go from 3 to 5. So my delta x value is not the same anymore. It's going to equal 2. And then our next interval is going to go from 5 to 9. That delta x value is 4. And then finally, we're going to go from 9 to 12. And 9 to 12 is going to take us back to a delta x value of 3. And that's actually going to be true for each and every single one of these 3 methods. So the 3, 2, 4, 3 as a progression of our delta x values, that's going to be something we're going to use each time. So for the RRAM, we're going to use, let's highlight that in yellow. We're going to use RRAM. We're going to use, between the 0 and the 3, we're going to use the 3's height of 16 because that's the right endpoint of the rectangle. That's what the first R in RRAM stands for, is right. And so we're going to use the 16 with the delta x of 3. We're going to use the 24 with the delta x of 2. We're going to use the 30 with the delta x of 4. And we're going to use an 8 with the delta x of 3. So we'll just write that out. We're going to have the integral from 0 to 12 of f of x dx is approximately equal to 16 times 3 plus 24 times 2 plus 30 times 4 plus 8 times 3. And we just have to evaluate that, and that's really all it is. 16 times 3 is 48. 24 times 2 is also 48. 30 times 4 is 120. 8 times 3 is 24. And then when we add those up, that's going to be, I think, 240, perhaps. So when we move on to the second method, the LRAM, it'll be essentially the same process, but when we do LRAM, we're going to use not the 16 for that first interval, we're going to use the 10, because that's the left side of that particular interval. Then we're going to use the 16, and then the 24, and the 30. Notice that we don't use the 8. So in the first example, we did not use the 10. In the second example, we will not use the 8. Everything else stays pretty much the same. We're going to say that the integral from 0 to 12 of f of x dx is approximately equal to, instead of 10, we'll use instead of 16, we'll use a 10, but the delta x is still 3. And everything just gets shifted. So 10, and then 16, and then 24, and then 30. And so the 10 times the 3, the 16 times the 2, the 24 times the 4, and the 30 times the 3. So this is just another basic arithmetic problem at this point. 30 plus 32 plus 96 plus 90. 180, 188 plus 60. Oh dear, 188 plus 60. Can't do that one in my head for some reason. So that's going to be 248, I hope. Alrighty. Notice we don't get the same value. We didn't expect that. It's possible that LRAM and RRAM will give us the same output, but we wouldn't expect that. They're two different methods of approximating the same value. And then finally, our trapezoidal method, well, that's going to use the 10 and the 16 in the first trapezoid. It's going to use the 16 and the 24 in the second trapezoid. It's going to use the 24 and the 30 in the third trapezoid, and it's going to use the 30 and the 8 in the fourth trapezoid. So this one's kind of nice because we're going to end up using all the different possible values. And just like we saw in that first example, the middle three values of 16, 24, and 30 will get used twice. The endpoints of 10 and 8 will only get used once because those are only heights of one trapezoid each, right? The 10 is the left edge of the left trapezoid, and the 8 is the right edge of the right trapezoid. So there aren't any shared sides with the 10 or the 8. But we're still going to have a 1/2 for each and every single one of these. So I'll factor out the 1/2, but we can't do that 2 times 16 plus 2 times 24 like we did on the last example because the delta x values are not constant. So be careful here. We're going to go ahead and do 10 plus 16. That's going to be times the delta x value of 3. And then we're going to do 16 plus 24 times the next delta x value of 2. And then 24 plus 30 times the next delta x value of 4. And then lastly, we have 30 plus 8 times our last delta x value of 3. So that would be, once again, just some basic arithmetic after we get it set up. So we'll go ahead and work out that final answer. We've got 1/2 times 26 times 3 is 78, I think. We've got 40 times 2 is 80. And 54 times 4 is 216, I believe. And 90 plus 24 is 114. And then we add those up and cut it all in half, and we get our final answer. I got tired of doing this all in my head, so I paused the video and I pulled out a calculator to figure out that when you added those up, you get 488. And half of 488, I can do that without a calculator, is 244. And you might notice a relationship between these three answers now, and I'll let you think about that.